Yeah, it's working, right?
Yeah.
Okay.
Hello, everyone, and welcome back. Thanks for being here for the last talk before the coffee break. This next presentation will be on Pass the Hash Toolkit for Windows Present. Sorry, my mistake. Just testing. This next presentation is actually on analysis and visualization of common packets. Packers. My apologies. Mr. Ero Carrera, before we begin, allow me to correctly and accurately introduce you. Ero Carrera is currently a reverse engineering automation researcher at Zynamics GmbH, formerly known as Sabre Security. Ero has previously spent several years as a virus researcher at F-Secure, where his main duties range from reverse engineering of malware to research in analysis automation methods. Prior to F-Secure, he was involved in miscellaneous research and development projects and has always had a passion for mathematics, reverse engineering, and computer security. While at F-Secure, he advanced the field of malware classification, introducing a joint paper with Gergely Erdely on applying genomic methods to binary structural classification. Other projects he's worked on include seminal research on generic unpacking. Certainly quite a mouthful, but ladies and gentlemen, do join me in welcoming Mr. Ero Carrera today.
Thank you. So today I'm going to talk a little bit about that last part that she mentioned, about generic unpacking and techniques, and about the specific techniques that packers use to make our life more difficult. And I'm going to focus a little bit on some of the hard ones, on like packers like Temid and Armadillo, and some of the techniques they use to make debugging, tracing, reconstruction of the process the hardest. So first I'm going to give some sort of historical perspective, how we got here, how packers actually came to be, right? So originally the idea of a packer is exactly what the name says. They were meant to just like get an executable and make it smaller. They were aimed at, when you had like bulletin board systems and you wanted to like get binaries running around and still downloading something was, the size of it was important because you had to pay for bandwidth. So it was important to actually make it as small as possible. So that was the original idea of packers. And they were something as simple as just compressing the executable and then creating a new executable that the first thing that it ran had some sort of envelope that first decompressed the whole thing in memory. But they had no specific techniques. They weren't aimed at obfuscating the binary. It was just like compression. Obviously, once you had this setup, it was really easy to go a step farther and actually improve on that. Because compression itself can be considered as some sort of obfuscation, because if you are not aware of the algorithm that is used, you will try to open the binary as it comes from file into some sort of tool, and you won't see the real code. The real code is, later on after execution, it exists in memory, but does not exist in the original binary. So, although really, really simple, it could be considered some sort of obfuscation. So, when they started actually to worry about protecting the binary, because they started charging money for the binary, so they started to put algorithms that they cared about. So they wanted to protect that. They wanted to protect intellectual property, and nowadays that's something that we see in all commercial applications. They want to protect the actual executable code because it contains algorithms or it contains processes that are important for the company that actually makes the application. So at that point, once you had the setup, it's really easy to think of ways of actually making it harder. Once you have something that takes control before the original application takes control, you can set up some sort of algorithms, some sort of techniques to actually prevent other tools from attaching to that process, damping it or manipulating it, or actually looking at the real code. So I'm going to first go now through some of the techniques that have existed over time, some of them more recent, some of them older, in order to make the life of the analyst harder, or the life of the person who actually wants to look at the original code. Or not. Just a second. Everything has frozen, so okay, it's still alive. So Into the techniques. The most important thing at first, and this is really simple, is to destroy as much information from the binary as possible that would help you to get a clue of what it is. Specifically in malware, you want to destroy any sort of indication of the APIs it uses, because that exposes the functionality that it's going to use from the operating system, or any sort of strings. Pretty much anything that is clear text that gives you an idea of what the binary or executable might be trying to do, or might be, information that might be using. If it's clear text, maybe email headers, maybe whatever it might give you a clue of what the binary's purpose is. You want to try to erase and destroy that. So with a packer, with a compressor, that's pretty much taken for granted, because that's going to be compressed. It's not going to be clear text anymore. But still, the import table might be there, depending how you do the process of the compression. So if you want to actually protect something, you want to remove as much obvious information as possible. So one thing that all packers do is destroy and reconstruct later on the import address table in some way or another, because that exposes the whole functionality of the binary, the way it connects with the operating system. Depending how complex the packer is, they will just simply reconstruct the original table later on. That's really comfortable, because lots of tools then can just dump it. And you will have it in your memory dump, and with a little bit of work, you will be able to load that into some tool and take advantage of that full, nice import table. In other circumstances, in more complex packers, they will reconstruct it in a non-standard way. They would use different artifacts to, so even if you get a memory dump, it won't be totally straightforward to see that relationship between the binary and the APIs. And as we will see later on, in the case of Tomaida and some others, they actually go to great lengths into trying to obfuscate the fact that they're using APIs, and they would use really interesting tricks to make it non-obvious. And you will see that there's no straight jump into the APIs by themselves. And there's a whole category of anti-debugging tricks, which are aimed at making your life using a debugger as hard as possible, like making tracing hard by constantly triggering exceptions and making it really hard to step through the application, doing timing checks. So if they see that a certain algorithm is taking way too long, it could be because you're stepping through it, so they may actually misbehave later on. If they notice that the timings are not right, are not what they should be for a certain CPU, if it will be running natively on it. Other things, throwing interrupts that the debugger uses itself, and if they cannot capture it, the application cannot capture it because the debugger is running, then you know that something is wrong. You are being debugged. Then you can use, if the debugger is running in user mode, you can just use straight syscalls, which won't be hookable by the debugger running in user mode. You can check for hooks. You can just, if you have checksums for APIs, you can just scan the normal APIs in the DLLs and see if they match, to see if the debugger installs some sort of hooks. You can do a set of, there are millions of techniques to try to detect debuggers, user mode debuggers, and kernel debuggers, looking for strings, looking for soft ties, looking for certain drivers. There's a whole encyclopedia of those. So this is basically what we have got so far at the level of anti-debugging. There will be anti-environment techniques, which would be in certain companies, like antivirus companies, for instance, or anybody pretty much doing something with malware has a couple of VMware or other virtualization software boxes where they actually, at least do some sort of pre-analysis to take a look at it, or run it through some sort of behavioral tools that capture the APIs it uses to get a quick idea of what the malware might be doing. So in that case, lots of malware nowadays do actually try to detect virtualization environments, do the typical blue pill thing, or go into a little bit more complex techniques, trying to detect specific instructions that might not behave the same in a real system as compared as in a virtualized system. Certain instructions might be invalid in a real system, but might not trigger the corresponding exception if you run it in a virtual environment. So there's lots of things that are not perfectly emulated that you can try to use to detect a virtual environment, a virtualized environment, in which you might be being studied. So as a piece of malware, you want to avoid being studied, so you want to detect any kind of environment that could be controlled externally. Then we have the techniques against specific tools, as I just briefly mentioned before. If the tool is a debugger, then you can have all kinds of techniques trying to detect it, whether it's presence in memory. If it's a tool like AIDA, for instance, then you can have specific techniques to make the disassembly, for instance, harder, or in the past there were problems where you could actually break the P parser depending how your P headers were constructed. But that problem was fixed. Some of the analysis problems are just hard to fix by themselves because it's not decidable entirely whether it's one thing or another. It could be disassembled in different ways, so you just have to know the right one when you're working with it. So you can try to break all of these tools, break others like ProcDam and SoftIce. You can actually, so some of the old ones like ProcDam, you can actually break them by erasing or once you're loaded in memory, writing different values in the headers in memory. So when ProcDam trusts the headers in memory to the dumping of the process. So if you put really large values as some of the sections, ProcDam will try to dump 2 gigabytes of memory and probably not be successful. So it will crash. So that'll be another set of techniques. Then we move into the more interesting stuff, which is anti-analysis. Anti-analysis will be something that is meant, whether you are analyzing the application like with a tool like IDA or even a debugger, this will make the actual comprehension of the application harder, just because they insert junk code. So between like a small function, you could end up with a really, really large function with the same functionality with a lot of useless code, but not obviously useless code. You will see operations being done, in the end they will cancel out, but it's not obvious for a human as seeing the assembler that will cancel out. You will need automated tools to actually to simplify all that out. Things like using opaque predicates, for instance. I will cover that later, so I won't go into detail now. But that will obscure the execution, the flow of the application as well. Then there will be things like code transformation and virtual machines, where the actual code of the application, the code that you're seeing, is not the code of the real application. It's the code of the CPU that emulates a real application. I will go into that into detail later. And then other techniques that do flow obfuscation. One thing that you do, and that's very common, is using exception handlers to divert execution. So when you're trying to debug the application or walking through it, you won't see the normal flow, like just a call, a jump, a normal branching. The flow is directed or is controlled a lot by throwing exceptions, like call a specific exception handler that you need to know what it is. That exception handler might do some other techniques trying to detect something, doing some checksumming. I mean, you can put whatever you want there. Some packers do checksumming on their own code in the exception handler to verify that everything is coherent in memory. And, but it makes it harder to follow because it's not just a continuous like flow of instructions. It goes jumping all over the place. Other things like Armadillo's nanomites, which I will cover in detail later, it's a really nice technique and makes the flow analysis itself kind of much harder. So for what I'm going to be explaining later on, the tools that I've used that allowed me to look into this at a high level enough to not have to worry about the small details and the anti-whatever techniques, where Box, I use this a lot. It's a full CPU emulator. So it gives me like a really, really high-level view of everything. The only problem is that I need to work and remove all the stuff that I don't care about because I see everything. I see all the OS, I see all the kernel executing, I see every single application. So I need to have some infrastructure to just focus on whatever I want to look into. But the good thing is I don't need to worry about lots of VMware detection. I don't care. Virtual PC detection. I don't care. Not that they couldn't detect Box, but nobody's been looking into it so far, unless in depth. So I can run armadillos, Timidas, whatever, and they just run fine. So that's really cool. So you can trace them. You can do all kinds of in-depth analysis of them. WinDebug as well is one of the more powerful debuggers, and it's extremely useful to just hook into the kernel mode, debug, and then you can look into applications that are really, really low level of granularity. As well, it deals extremely well with complex exceptions, things that Oli cannot really handle. I was sometimes looking into Armadillo, and in some parts of the code, just Oli cannot handle certain exceptions. Cannot really pass them back to the application and handle them properly, while WinDebug didn't have a problem whatsoever. And if you're really hardcore, you can use Peter's Memorize. That will allow you as well to get the real dump of memory and work with that a little bit in the same way that the kernel level access of Box or WinDBG give you. So all of those are really good tools to play with stuff at the low level. Both, well, as you saw, Memorize can actually give you physical data, like freely from the physical address, as well can WinDBG and Box, and that's a really interesting aspect of exploring the machine at the physical level. There's lots of tricks that don't matter then. So now I'm going to move a little bit more into detail and explaining some of these tricks, some of the more interesting anti-analysis and obfuscation tricks. So most disassemblers will actually have some sort of logic to go through this assembly, obviously. So they will collect a set of entry